for having me. Yes, Mattia is defending in a few hours, so he'll be officially a doctor by this afternoon US time. So it'll be me giving this presentation. A good part of this work is out of his master's and PhD with me. So we're going to talk a little bit about how we can use barrier functions in the context of model reference adaptive control, and in particular time-varying barrier functions, and then how we can apply these theoretical results in practice, in particular, to unmanned aerial vehicles. So the context we're working on is the context of MRAC, model reference adaptive control. And in particular, what we want to do, which is not able, which couldn't be done yet in the literature, before our work was to have both hard and soft constraints enforced by an MRAC system, hard constraints on the tracking error, as well as soft constraints such as actuator constraints. The hard constraint problem was already solved, but at the cost of having very aggressive control inputs. Then existing methods on constrained MRAC rely on barrier-Lyapunov functions. And in some cases, they use the barrier-Lyapunov functions to enforce the rate of convergence of the tracking error to zero, or equivalently of the closed-loop plan trajectory to the reference model. However, this approach, the approach of using barrier functions to enforce the rate of convergence on the tracking error, can be particularly aggressive. So we address this problem as well. And finally, we address the problem of how to mitigate the fact that multiple constraints on multiple aspects of the control system, such as the tracking error or the saturation, may be competing to each other, right? Because we all know that, of course, if you're going to have a higher tracking error, you may need to also have higher control effort. So what we want to do, we created a control system, an MRAC system, that enforce hard constraints on the tracking error, soft constraints on user-defined parameters, such as the saturation of the control input. And we will be referring to this problem throughout the presentation, although the saturation of the control input can be replaced with whatever other soft constraint you would like to impose. Mediate, again, between hard and soft constraints. Be robust and matched uncertainties. We'll discuss this kind of uncertainties, which is among the hardest, definitely for adaptive controllers in general, and MRAC in particular, and then enforce the rate of convergence without using barrier-Lyapunov functions. So we want to use barrier functions to enforce the constraints on the tracking error, other soft constraints, however, not to set the rate of convergence. And then decoupling the tuning of the convergence rate from the tuning of the reference model, which has been a key issue in the adaptive control community that led, for example, to the development of L1 adaptive control or other forms of modifications of MRAC that have been fairly popular in the past decade. So for those who are not familiar with MRAC, here's a quick overview. So we basically have a plan model in this form where the matrix A is unknown, the diagonal positive definite matrix lambda is unknown, and then nonlinear terms are assumed to be matched, which basically means that they go through the same channels as the control input, and they're divided into two parts: a regressor vector that can be physics-based or produced by a deep neural network, whatever method you like, and then a matrix of coefficients that there is unknown. Of course, not all uncertainties can be captured this way. We'll discuss a more general model in a couple of slides. So despite the fact that we don't know A, lambda, and theta, we want to find a control input U such that the state X of the plant follows the reference trajectory xref. And xref basically is the solution of this model here. Now, in MRAC, we can see reference models either as a filter of the reference command input R, which is a bounded continuous signal provided by the user, or it can be your ideal model, right? So say the plan model is your actual aircraft and xref is your ideal aircraft, and you want the actual aircraft to behave like the ideal aircraft. controlled by the pilot, right, our command. So again, we want to send the tracking error e to 0, subject to some conditions, matching conditions, which sometimes they're called compatibility conditions. Those who are not familiar with MRAC sometimes are a little bit disturbed by the matching conditions. But these conditions basically are necessary to guarantee that there is at least one solution to this problem. Imagine that your plan model is a car and your reference model is an aircraft. There's no way on earth you can make the car take off, right? Because you don't have the actuators. So the matching conditions won't be solvable. Now, you cannot solve the matching conditions because you don't have A and lambda, but you need to postulate that those can be solved if you knew A and lambda. In problems of practical interest, this can almost always be done because you know which elements of A typically are zeros, and we know the structure of lambda, which you assume it to be diagonal positive definite, because the only role of lambda is to capture basically underperformance of your actuator system, right? Then the controller is basically in this form here, where the adaptive gains are kx hat, kr hat, and theta hat, which are regulated by these adaptive laws. Now, this is the standard textbook solution to the problem that dates back to the 70s or late 60s and has many, many problems, but we're not going to discuss it here. It's just to introduce classical MRAC. A variation of this method, which dates back to 2011, allows to accelerate the rate of convergence of MRAC in a user-defined manner. A typical problem of MRAC in the class of MRAC solutions, again, the one I showed in this slide is the most basic one, is that basically it can be proven that the closed loop plan model converges to the reference model after the transient of the reference model has died. And so this is a problem because we spend so much time shaping the reference model through RF, and eventually we mimic the ideal model only after the transient, which to some extent is almost the most fun part, has decayed. So we don't want that to happen. So we want X to converge to XREF before the transient of XREF has decayed. So my group 10 years ago or so came up with this technique. It's called two-layer, where basically we introduce an additional reference model, an auxiliary reference model, which is totally user-defined. And basically, the role of this auxiliary model is to accelerate the closed-loop trajectory tracking error, such that basically the convergence is set by the user. How does the user set the reference model, the auxiliary reference model, and the rate of convergence? Basically, the user can choose the eigenvalues of this matrix A tran such that they adhere to the left to the eigenvalues of the matrix RF that characterizes the primary model, the primary reference model. The farther the eigenvalues of A tran are on the left to those of RF in the complex plane, the faster will be the convergence of the tracking error to 0, or equivalently of the plan model to the reference model. So what happens is that we need to introduce an additional variable epsilon, which is basically the difference between the actual tracking error and the second layer. But we all see that A tran is Hurwitz, and so E tran converges to 0. So after some transient, epsilon and E are pretty much one and the same. We modify the control load by adding the MRAC control load by adding an extra term and an additional adaptive load for kg. The structure of the adaptive loads remains the same. However, instead of referring to the tracking error E, we need to refer to the auxiliary tracking error epsilon the whole time. But conceptually, not much has changed. So here is the problem, a little bit more generic, but with the key difference is this term here, XCD, the so-called unmatched uncertainty. Well, XCD plays a pivotal role because it's not only the term that captures any external disturbance, but it's also the term that captures whatever is not being captured by your physics-based regressive vector phi or your neural network-based regressive vector phi, right? Whatever technique you want to use to reconstruct your uncertainties, that technique can't capture any possible action on the system, as well as a nonlinear term, right? There's a whole learning theory about that. So there's always going to be some error, and this error is basically captured by the unmatched uncertainty. A famous problem of the unmatched uncertainty is that although you may send the tracking error to a small value, the adaptive gains may experience so-called parameter drift, which has been a serious issue that put a halt on the research on adaptive control in the 80s till this problem was seriously solved. The most common solution is to use the use of the continuous convex projection operator, where basically we take the usual adaptive laws and then we constrain them without entering the math details because it's out of context for today's presentation. But what the projection operator does, it basically creates two constraint sets of identical shape that are convex, an inner one and outer one. As long as the adaptive gain lays in the inner set, this gray set here, we use the usual adaptive laws. If the adaptive gain is between the inner constraint set and the outer constraint set, basically we start trimming the radial component of the adaptive gain, such that in a limit case where the adaptive gain reaches the boundary of the outer constraint set, then the normal component of the adaptive gain is trimmed completely to zero. And this is done in a continuous manner, which is a great advantage. So basically, the blue ellipse in this graphical representation is a hard constraint on the adaptive gains, and this prevents parameter drift despite this term over here. So of course, we can only guarantee uniform ultimate boundedness of the trajectory tracking error, and the ultimate bounds essentially depends on the unmatched uncertainty. But from an engineering point of view, we obtain satisfactory results, which are compatible basically with our ignorance on the external disturbances. The two-layer formulation is pretty much identical, so I'm not going to go over that. But this slide basically summarizes the key contribution of our work today's work from a theoretical point of view. So we have not only the projection operator, but we also compound the so-called dead zone modification of M. And this is the effect of this mu function over here. So basically what happens here is that if the tracking error is sufficiently small, there's no point in adapting. I mean, we're just working hard for improving results just a tiny bit. So if the tracking error is sufficiently small according to our liking, then we can basically turn off the adaptation and move on. Now we have a new entry here, actually two new entries compared to the previous slide. As you can see, here we have gamma, the adaptive rate, x, r or phi times the tracking error times pb, where p is the solution of the Lyapunov equation. Now we have this term here, h, and this term here, b. Those are related basically to the constraint set. So in this work, how do we capture the constraint set? For us, the constraint set is the set of all epsilon such that this h function is positive. Now, for this work in particular, the h function for us has a specific form, which is eta max, which is an upper bound given by the user, minus epsilon trans plus m epsilon. Again, when you read epsilon, read tracking error, basically. And so it's a weighted square norm of the tracking error. And then we have this term here, negative eta squared, which basically is a function that we're going to choose adaptively that regulates the diameter of the constraint set, right? So the bigger eta, the smaller the constraint set. So for this reason, we call this constraint set funnel, because ideally the constraint set will continue shrinking over time, giving basically the shape of a funnel, right? In reality, it's not going to happen, but or it's going to happen only when the situation, when we have favorable conditions, and we will discuss this in a minute. And so the term dE is our Berle-Lyapunov function, which is given by epsilon transpose PE, the usual Lyapunov expression for most linear systems, over h, which is again our constraint function. So it's time to introduce an important actor for us, which is this term xi, not to be confused with xd. This is the disturbance. This is something else. which basically is a function that captures the soft constraints. So the constraint set epsilon that we have over here, or script E that we have over here, is a hard constraint set. So we can't violate this constraint no matter what. But now we introduce also soft constraints which should be accommodated, but we don't accommodate them only if strictly necessary. And for example, if you want to enforce constraints on the saturation, we can do something like this. So we want U in norm not to be smaller than U mean and not to be larger than U max with a certain um, uh, um, threshold or tolerance delta U mean. So how do we choose the diameter of the funnel of the constraint set? So we do so adaptively. So we have basically an adaptive flow also for the constraint set. I'm not going to go through this math formulas. I mean, it's not the case for an oral presentation. But I'd like to point out that basically we have this lambda sat term that appears in sigma norm, which is what drives the adaptive flow, which basically says, well, if your system is able to accommodate this kind of constraints, the dynamics of the system is able to accommodate a constraint that gets stricter and stricter, then do so. Otherwise, keep the constraint as is or relax it as much as possible, waiting for for a more favorable condition. So yes, I'll stop. Okay, I just got a message saying I was informed that we have to stop at 15. 5:30 Eastern. Okay.
Sorry, just like that's like
Yeah, okay. I'll wrap up, I promise. Um, so here's a graphical representation of what's going on here. So basically, the user says the tracking error cannot go beyond eta max no matter what. And in reality, because we need to account for digital implementations, we're going to give a certain buffer, which is delta 1, such that when we implement this continuous time formulation in a discrete time formulation, we don't violate the constraints. And so the boundary of the constraint set is represented by this red line. And again, to account for digital implementations, we don't want the weighted tracking error to be delta 2 closer to the red line, the boundary of the constraint set. Now, if possible, we try to reduce the constraint set as much as we can, as it happens in these gray banded areas. However, there may be some situations in which, for example, enforcing those hard constraints on the tracking error may require too much control effort. So the actuators may start saturating. So we try to relax the constraint set a little bit and see what happens. And so the red line increases a little bit, but then in some situations, we get way too close to the hard constraint imposed by the user. So at that point, the actuators will need to start suffering a little bit. And so basically, we stop the growth of the constraint set and see what happens. If a more favorable situation arises, then we keep shrinking the constraint set. On the other hand, we don't want to shrink the constraint set way too much because that may start producing a lot of stress for minimal improvement. So at that point, basically, the constraint set will not go below delta 3, which is larger than some minimum requirement given by the user. And so this is your happy area, right? If you're here, your system is doing well enough from an engineering point of view. I remind you that we're using the projection operator to constrain the adaptive gains and hence implicitly the control input. So it's not an explicit constraint on the control input, the use of the projection operator, but it's sufficiently good. And in most applications in adaptive control, that's how basically we enforce constraints on the tracking error. So let's go through numerical simulations. When we started this project 3-4 years ago now, we asked ourselves what are good simulators for UAVs, in particular multi-rotor UAVs. We were looking for something that was suitable for control applications. What I mean by that, we wanted something that for which we didn't write the equations of motion ourselves, that was able to account for unknown payloads, moving payloads, sling payloads, interactions with the environment, and that was reliable. So we did a literature review, and it turned out that most of the simulators out there are primarily for guidance or navigation purposes, but not necessarily for control. Here's a short list of those we surveyed, and eventually it turned out that there were three simulators that worked the best for our purposes. The last two explicitly designed for UAVs. However, they didn't have finite element methods or didn't allow for contact forces, didn't allow for sling payload, and in the case of flight mare, there's basically no documentation, which makes it extremely harder to manage. We landed on PyChrono, which is a high-fidelity finite element-based simulator that is developed primarily for mechanical engineering problems for ground vehicles. We've been the first ones to port this to a UAV environment. In fact, you see that it was marked as UAV really oriented as no, because that was not the case before our work. So what we did, the way it works, basically we import a high fidelity CAD model of the actual vehicle, and then we launch a mission, and we can do things like, payload dropping, moving payload, and stuff like that. We tested this on, for example, on a PC with 14 cores and 20 threads. And what we can do, we can run up to 20 simulations, for example, if you have 20 threads available. And so we can run hundreds of simulations at the same time and see how our controller performs in multiple scenarios. So this is completely freeware. It's available on GitHub. So if you can connect to our GitHub through this QR code, and the slides are available. And so, as I said, you can run hundreds of simulations and do parametric studies, for example. These kind of controllers have many tunable parameters. So we want to see what happens if we change some parameters and what's the sensitivity of the system to some of these parameters. So here's a quick video showing you, for example, how the control system we discussed earlier performs over two other control systems. 7 is a non-robust version of what I presented to you today, so without projection operator, but that's on modification. And 8 is a similar control system. And as you can see, we're transporting two balls in a container, which are totally unknown to the control system. So what we did, we tuned the controller without the payload, then put in the payload and asked to follow some trajectory. And as you can see, the theoretical framework we showed earlier allows very good tracking for our control system. Another one didn't do well at all. It crashed, actually. We cut the simulation because it crashed. And then a third method, didn't do as well in terms of tracking error. Likewise, we do not only in terms of tracking error, but also in control input, because the trust is extremely similar between the two. Mind you that the trust model that we use is experimental. We characterize actual propellers, created an analytical model of the trust model of our propellers, imported it in the controller, in the simulator, and so it works. And here is, one of the representations of our constraint system. You can see the tracking error is down here, and the funnel diameter is over here. You see it contracted a little bit. It grew at the beginning to accommodate, the takeoff effort, and then it contracts a little bit over time. And then we tested our results experimentally. So we tested it on an Odroid, which is a single board computer installed on a UAV. It talks to a PICSOC that serves basically as a coordinator of our propellers. And then basically the way the system works, we have the Odroid that manages the control thread. It takes data from motion capture system or onboard cameras, depending on how you want to fly. And the PICSOC has a Kalman filter manages the sensors, manages the information coming from the onboard cameras for localization or Vicon, and it manages the propellers. Also, this flight stack is publicly available. It's on our GitHub, and anybody's feel free to contribute. We have detailed wikis so that anybody can reproduce our results, and we store also flight test results for reproducibility purposes. So this is our vehicle. It's the actual vehicle that you seen in simulation earlier, and we added a sling payload, which is this ball over here. And if you have this thing fly, you'll see that. Sorry, I need to. So these are 9 flight tests. They're all different, and you can see the vehicle following certain trajectory and then landing back on the on its land pad in nominal conditions. And then here what happens with a classical formulation without the control architecture I showed you earlier, and the performance is it's not comparable. We'll see that in actual flights when we will see the plots. And if I go ahead and compare the performance of the two controllers, you can see that ours is definitely much smaller control tracking error, not only as an average, but also point-wise. As you can see, we plot the standard deviation, and the pink area is consistently above the blue one. In off-nominal condition, we're carrying our a little ball, as I showed earlier, and the vehicle is able to follow. The vehicle is able to follow its reference trajectory very well, despite the fact that we have a payload that is 30% of the total mass, and the actual vehicle. With other techniques, we don't do as well, and these are the results showing the quality of performance. Here are plots showing the behavior of the constraint set. Again, the user, we set that the constraint set could never go beyond this point over here. And actually, you see the funnel contracting sometimes. In some cases, it has to expand a little bit to accommodate some extra control effort. And this region is pretty much where the UAV turns around. But we can see that eventually the tracking performance is always satisfactory. In some cases, it drops below the non-adaptation point of the other constraint set. As you can see, these are the L2 norms, and we can see that even in off-nominal case, our controller does better than the nominal case of other techniques, which is really impressive to us. And as you can see, also the control effort is smaller, which is quite interesting. So we not only do better tracking in terms of tracking error, but we do better also in terms of our control effort. Anyways, that's pretty much about it. Feel free to shoot me an email if you have any questions. This work was partly supported by an external grant. And again, here are the QR codes that take you to our sets of software, the simulator on the right, and the flight stack on the left. And a very interesting thing I would like to remark is that the gains that we obtain in simulation can be ported in flight with minimal retuning. That's a very interesting thing. We're going to work much harder on this in the near future, because basically we all know that if you do your tests in MATLAB, whatever gains you tuned in MATLAB can't be really ported in real life. MATLAB or any other high-level simulator are good to test the feasibility of an idea, but not for tuning purposes. Our simulator is so good again, we work hard on the CAD models, I give you that, but they give us a very solid starting point for the adaptive gains to test in flight, which reduces our sim to flight time and the number of hazards and accidents in flight tests. With that, guys, I think that's it.